Hello everyone, my name is Matt Cagle. I'm a PhD student at Mississippi State University in the Mechanical Engineering Department. And today I'm going to be showing you a tutorial for running a single Frank-Reed source in a body-centered cubic or BCC structure using the dislocation dynamics software MDDP. The software was developed by Dr. Hussein Zabib at the University of Washington, and it's a very useful software for visualizing dislocations within a crystal structure. The first thing you want to do is go to the main page for the ICME website at icme.hbc.msstate.edu and look on the left side of the page and find the Education tab and click on Mississippi State University. So now you want to scroll down and you'll see the course material for the previous years of ICME, and we're going to click on Homework 2 for 2017 as it pertains to the MDDP setup. And we scroll down in this file to find the dislocation dynamics section, and we're going to click on the MDDP real quick to show you a little bit more about MDDP and show you where the manual is. There will be several input files that I show you today, but I won't go over every single line as they're not important for the software simulation we're trying to run. But if you're interested in those values, you can click here and download the manual. Okay, so the first thing we do to get started is to click on this link right here in the environment setup, and you will get a zip file that contains applications and input files. So for BCC, we're going to select the BCC data executable along with the data and data in files and the MDDP 08 and copy those to a folder that we've named single Frank-Reed source. Okay, so now we're going to examine these input files and make the changes necessary. So you're going to want an editor like Notepad++, or if you want to use Notepad, that's completely fine, but we're going to look at this data in file. Okay, so here we have the data in file, and the first thing is we need to select our cell size for the simulation. So you want to pick something that will allow you to see enough dislocation loops that satisfies what you're trying to run. So you want the 10,000 by 10,000 by 10,000 Burgers vectors, and this next line you want to leave for 0 that actually comments out the next line, because this is not important for the software we're trying to run today, and neither are the rest of these lines. But if you read the manual, they have different roles for different types of simulations, but in our case we're not going to change them. If you have different values in the data in file that you downloaded, then you need to change those values to these for the simulation of a single Frank-Reed source. Okay, so now we've saved that file, and we're going to pull up Command Prompt in Windows, and we're going to navigate to that file. So we say CD, and then we find our folder on File Explorer, we copy the path and paste it into Command Prompt, and now we're navigated to the right folder. So now we can make a call to the application BCC data, and the first thing it asks us is, do we have the data in file, which we just prepared and saved. So yes, we have it. We say 1. And now it gives you a list of options for what you want to simulate, and we want to select the 1 option for the Frank-Reed sources for BCC. And of course we're doing a single Frank-Reed source, so we say 1 pair. Okay, so here we're going to use the same values that Brad Huddleston used in his video for FCC using MDDP, and he used 1,000 for the minimum and 1,000 for the maximum, so it gives it the same length. And for the minimum separation distance, we're going to say 200 Burgers vectors, and 5,000 for the maximum. These are also the values that Brad Huddleston used. Okay, now it gives you all the different glide planes that are possible for the BCC system, and I'm going to select 5, the 110 plane, for our software, though you could choose any of 1 through 6 and still see a dislocation propagate. Now you want to have the random number generator, and you type in 1, 2, 3, 4, 5, 6, and that's going to propagate your dislocation location within your structure. And since now we've propagated our information and we are finished with this section, we'll say 1 for yes. Okay, so now we'll enter the year, which for right now is 2019. And for the maximum segment length, we're going to leave it at the default value of 100. And now we want to pick a strain rate that is fast enough for our software to propagate the data in a reasonable amount of time. So we're going to say 1 e to the 5. And we're going to choose our loading direction to be 1, which will be the x direction. We'll explain that later on. Okay, so the loading condition, we want it to be a constant strain rate, so we say 0. Okay, so with that, we've generated our MDDP file, and we can look back at the Notepad++ editor and see what we generated. So we navigate to our folder, we find the DD input file, and here it is. Okay, so we need to change a few things in this file to make sure we just have a single Frank read source instead of a pair. So you're going to want to change the 4 here to 2 to have 2 nodes that represent one Frank read source. Okay, the 100 is what we inputted for the burgers vector, and this is our strain rate of 1 e to the 5. Okay, and this is our loading direction of 1, which is the x direction. In the next line, we have this input for our time step, and in Brad's tutorial he is prompted to put this in, but we didn't have that prompt, so we can put in the same value that he had, 1 e to the negative 12. Okay, so we don't need to mess with the strain tensor or the stress tensor, but we need to change these coordinates for this location a little bit. So this is your x, y, z within the structure, and this is the x, y, z for the burgers vector. Now you just want a single Frank read source, so you need to delete 2 of these lines. Okay, so you also need to change the z value to 0 for the burgers vector. This is going to allow the loop to propagate within the plane so that it doesn't go out of plane and actually completes entire loops. Okay, for line 6 you want to also delete the last 2 lines so that you only have 2 lines, one for each node, and change the number and the connectivity a little bit. So you want to go with 0, 2 and 0, 1, 0. That is going to be describing the nodes and that they're not connected to each other. Okay, so for the plane it is selected as 5, 5, the constraint is 7, 7, and the slip type is 4, 4. So now our DD input file is complete. We will save that. And now we'll take a look at the data file. Okay, the data file needs to be set up for BCC, having BCC right here. And here is your time step maximum. That is when the program is going to terminate. And you just want it to be high enough that you're going to see enough usable data. And for the X, Y, and Z, this needs to match our data in, which it does in this case, 10,000, 10,000, 10,000, to make sure that you check that. Okay, so in the second line we have the material parameters for the material we're trying to simulate, and in this case it's chromium, which is BCC. We have the density, the shear modulus, Poisson's ratio, mobility, and the burgers vector. The mobility was calculated from the slope of the velocity over the shear stress applied that you did in part 1 of homework 1, and that is divided by the burgers vector to give you 1 over Pascal seconds. And you want to make sure that this value is somewhere in the hundreds or in the thousands, and if it's much higher than that or much lower than that, you may want to check and make sure that part 1 was simulated correctly. In the third line we have an input for temperature, which in our case we're going to leave at 300 K like Brad did in his video. And the stacking fault energy for BCC, it is going to be the very top of your curve, the highest point. And so for us it's 1.338 for chromium. And these next few parameters we're going to leave the same. We don't need to change them to run our simulation. And we're going to skip down to number 8, lines 4 through 7. We don't need to change, but again, if you have different values than what I have here, you may want to change those values to reflect this type of structure. Okay, so in 8 we have the coordinate system, and here is kind of how we pick the loading direction. And so for X we said 1, 0, 0, and for Y 0, 1, 0, and for Z 0, 0, 1. Okay, and 9, here is how often it's going to print results, and each 100 time steps you're going to see results on your command prompt. And that's enough for it to be frequent enough to see how the program is doing, but not too infrequent that you get large jumps in your data. Okay, so you want to, and for line 10 you just want to leave these values as is. Alright, and now we save our file and we can go to command prompt, and now we can run MDDP. Okay, so you just want to type in MDDP 08.exe, and it's going to propagate all of our information that we just entered, and we hit Y for yes, and it starts running. Okay, so for these simulations, they're not going to take very long to run, maybe 30 minutes at the most, but if you're just simulating one Frank Read source, it should probably be on the order of 5 to 10 minutes. So if it takes much longer than that, then you probably have something wrong in your script. Okay, so now I'm going to show you kind of what it looks like just out of the box when you run it. So when you download TechPlot, you want to go to File and Load Data, and you want to find this DD time results that has generated in your folder that you were running these applications. That file is going to be very important for visualizing the data, and this TechPlot file is going to be for the actual visualization, which there is a tutorial on the ICME webpage for using TechPlot, and there are also clear instructions that have been written by Brad Huddleston in the MDDP section. Okay, so we select DD time results, and now we're going to make sure that it's the TechPlot data loader that loads. We say OK, and we replace the data. So here we have our dislocation density and the time now, and you see that it's slowly growing, which makes sense. Our loops are propagating. And we want to change the mapping style. Our X variable we're going to set to strain, and our Y value we're going to set to stress. And we will close that. And now we need to go to plot and hit axis and reset the range, reset to nice values, and then click on X1, reset range, reset to nice values, and say close. And we see a linear relationship of a stress strain plot. Okay, so one more thing before we finish this video. I want to go back and show you a few more links. Here are the post-processing instructions for MDDP that I talked about, and they are just written instructions for how to use TechPlot, though there will be a tutorial video hopefully available after the spring of 2019 ICME. Okay, and the other link is for the FCC structure, which if you're trying to simulate FCC, you can watch Brad set up a simulation for the single Frank Read source pair. Okay, with that, I believe I've shown you everything you need to know to set up a single Frank Read source using BCC data. I thank you for watching this, and good luck.